Hello, in this lecture I will talk about force vectors and in general vectors operations. Let's look at general application and what we're trying to achieve and what we're trying to learn. By learning about vectors and their operations and force vectors, you should be able to identify and solve problems such as the pictures that you're seeing here. The tension, which is the pulling force, in each of the cables that you're seeing in these three cases could be found and analyzed by using the concepts that we're about to learn in this chapter. I'm sure most of you know what is the difference between a scalar and a vector, but let's just go over it one more time. Scalar is any positive or negative physical quantity that can be completely specified by its magnitude. This is an important word that we are going to be using a lot throughout this course. Magnitude. Can you think of some examples? Some physical quantities that could be completely specified by its magnitude only. Length, or mass, or time. Okay, if someone tells you 20 feet, that's all you need to know. If someone tells you 20 kilograms, that's all you gotta know. If someone tells you 2 minutes, 2 seconds, that's all you gotta know. In the other direction, we have vector. Any positive, or let's say any physical quantity that requires both magnitude, we still need magnitude, and something else to be completely specified. Okay, I'll let you think about magnitude and what, and I'll give you some examples here. Force, which I'm going to talk about next, which is pulling or pushing. When I talk about pulling or pushing, I'm talking about direction. So a scalar, magnitude is enough. For a vector, we need both magnitude and direction. Some other physical quantities that we are going to talk about in this course: position, moment, which we're going to learn later. But now let's focus on force a little bit more. Okay, force is action of one body on another. Okay, in simple, it's just the pulling or pushing that is applied to a body. Okay, we usually characterize force by its point of action or point of application, by magnitude, it's a vector, by line of action, and by its direction or sense. Okay, let's look at this. In the book and in this course, we always show force by an arrow. Point A is point of application, but it's also called tail of a vector or tail of this force. Usually the length of a vector shows its magnitude. When we draw a vector or a force longer, means it has a bigger magnitude, and when we draw it shorter, it means it has a shorter magnitude. The end of it, or the arrow, is called the head of the vector. The angle is between the force and usually a fixed axis, which we can have different axes, and we're going to talk about it. But one important thing that I want you to remember, which is very important and it's going to come in handy later, it's line of action. And line of action is on both sides. It's not just on the point of application. It doesn't matter where the point of application is. This line of action goes to infinity from both sides, and we are going to be using it. In this course, the notation I'm going to use, let's call this A. I will be using force A or vector A with a little arrow on top of it. So whenever I show an arrow, that means it is a vector or it is a force. And if it doesn't have the arrow, means it's just the magnitude. Okay, let's look at some vectors operations. But before doing that, I want to introduce you to one of my favorite books that I have. It's called 101 Things I Learned in Engineering School. And usually I read paragraphs from this book to my students, but I decided to include it in this video. It talks about interesting engineering facts, usually applied to life, and makes you think about what's going on around you. So now that we learned about vector and vectors, that they have a magnitude and direction, it says here that you are a vector. What does that mean? So a force is expressed graphically by a vector. That's what we just did. A vector's length represents its magnitude, and its direction is given in relation to the x, y, and z axis, which we haven't talked about yet. Every person has a gravity force vector with a magnitude of the weight measured in pounds or newtons, and a direction towards the center of the earth. Any single vector can be replaced by more than one component. That's an important word, and I'm going to be talking about it in the next few minutes. And vice versa, as long as they yield an equivalent net result. Okay, so there are some key words here: magnitude, direction, vector. Anytime that we talk about vector, I want you to remember these two key words. It has a magnitude and a direction. And whenever you want to work with a vector, you have to consider both the magnitude and direction. I'm going to be talking about components of a vector and the result in just a few minutes. So let's talk about vectors operations. Again, vector, magnitude, and direction. So what happens if I multiply a vector by a scalar? Let's see. I have a vector A. What happens if I want to find vector 2A? 2 is a scalar, meaning it only has magnitude, so it will only affect the magnitude of vector A. So vector 2A, I have to draw it almost to double the size. Let's see, what happens if I want to draw half vector A? Again, that's a scalar, it only affects the magnitude. I have to draw it about half the size of vector A to show the magnitude is cut in half. See, the direction is not changed. What happens if I want to find minus 1 multiplied by a? So now this will change the magnitude, or I should say doesn't change because it's 1. And the negative is going to change the direction. So minus vector a is the same magnitude, is just the opposite direction. We're going to talk about vectors operation. We don't have a vector multiplied by a vector, but we have vector dot another vector and vector cross another vector, which we're going to talk about later in this chapter and later in chapter 4. But let's see how can we add two vectors together. So a vector plus another vector. Vector has a magnitude and direction, so we have to consider both of them. So we have to account for both magnitude and direction of those two vectors. So to do addition of vectors, we're usually using two rules. The first one is called parallelogram, or parallelogram law of addition. Okay, I have vector A, I have vector B. I want to add these two together. Step 1, do you remember what this point was called? It was called tail. So put the tails of the two vectors together. And then, let's see. From head of A, you draw parallel to B. Or I should say parallel to line of action of B. So this is parallel to line of action of B. From head of B, we draw parallel to line of action of A. Parallel to line of action of A. You find the intersection and you connect the tail of the two vectors to this intersection point. And this vector R is just addition of these two vectors. So before moving on to the next one, I want you to pay attention. This is a parallelogram. So what it means is this length, or vector B, or magnitude of vector B, is equal to this length. And this length, or magnitude of vector A, is equal to this length. So we're going to use this to introduce a second law, or second rule, which is triangle rule. We again have vector A, we have vector B, and we want to find A plus B. In this one, we move the tail of B to the head of A with keeping the direction. And now all you have to do is connect the tail of A to the head of B, and this is your vector R plus B. So if you look at these two laws, they're basically the same thing. I just told you that the length of this length equal to vector B. So let me redraw this. A, and then that length, and this is R, and I just told you that that length is vector B. So when you look at these two are basically the same thing. You can use the same rule to find or deduct two vectors from each other. Okay, all you have to do if you want to find A minus vector B, all you have to do is make vector B the opposite direction and add them together. Okay, so now let's see how we're going to use this and what is the application of these vectors operation and parallelogram rule. So these are the two major applications that I'm explaining here to you: resultant and resolution. Okay, so let's go first to resultant vector. Resultant vector is what we just did, what we just added two vectors together. This R is called resultant vector or resultant force. It's a result of those two vectors. So the application of it is something like this. You're lifting a load with a crane and a hook, and there are two chains. Let me draw it here. F1, F2. You are going to use parallelogram. So from head, you draw parallel to line of action of one. From the other one, draw parallel to the line of action of the second one. Find the intersection, and you find the resultant vector. So by doing this, now you have the effect of these two forces. So if you're designing this chain here, or this hook, this R is the amount of force that goes into that chain. So resultant is easy. The second application is a resolution. And that means you start with one force and you resolve it into two force that have caused that. And why do we do it? Here's a good example. Here we have a link that they're probably, let's see, they're connected maybe to a wall and to ground like that. Anytime I make a hatch like this on a surface, that means it's a fixed surface. So you have a force applied to a link or two links at one point, and you're the designer. You want to design each of these links and you want to see how much force is in each of them. In other words, how much force is in the direction of U that you're seeing here, how much force is in the direction of V. To do that, we have to use parallelogram in reverse, meaning from head of F, we draw parallel to our axis that we want to find the force in that direction. Find intersection with U, and then you draw from F, head of F, parallel to U, and find intersection with V. Make those intersection, turn those intersection into a point. And now from head, or sorry, tail of F, if you draw to that point, that is F sub U. The other one is F sub V. So let's see. Just going to draw it here. So before, let me show you here. Before I had vector A, vector B. I add them together to get vector R. Now what you're seeing here, I have FU, FV. They were added together to get to that vector F. The only difference is I started with that vector F. Let's put an arrow here to make him a vector. So vector F is just addition of F sub U plus F sub v. Same thing here. f1 plus f2 equals that resultant vector. So they're both the same thing. The only difference is here we start with 2. We start with this, we end with that one. Here we start with f, you end with those two, and that's what it's called a resultant and resolution. So these two are called components of vector f. These two are called components of vector r, meaning if we resolve r into two forces, we are going to get two components. So axis u and axis v are just random axes. One of them seems to be horizontal, the other one has an angle. We don't know. Special case when a force is resolved into two components along famous x and y axis. The components are called rectangular components. Okay, so force F or vector F here was resolved into two components, Fx and Fy. A very, very important point that I want to mention. From head of F, we have gone parallel to Y. This is very important. We have not drawn this perpendicular to X. Okay, so I want you to pay attention. It is perpendicular to X, but that's not how we draw it. We draw it parallel to Y. It is a very distinct, there is a very important distinction here that you're going to see in some problems. You should always go parallel to Y, parallel to X, and find the components. Just like we've been doing with parallelogram. Parallel to X, parallel to Y, find intersection Fx and Fy. Vector F, I have resolved it into two components, F sub X and F sub Y. This is a parallelogram, right? Meaning this length here is also F sub Y. In other words, I have something like this. I have Fx plus Fy equals F. And this angle that is making with x-axis is theta. So let's see. Cosine of theta is adjacent, which is Fx over F, magnitude of Fx over magnitude of F. Sine theta is Fy over F. So magnitude of Fx is F cosine theta. Again, this is magnitude. And magnitude of Fy is F sine theta. So these are just the magnitudes. Now we are going to use something called unit vectors. Okay, this I and J that you're seeing, I and J are called Cartesian unit vectors. Based on what you know, vector is something that has a magnitude and has a direction. So can you tell me what is the magnitude of I or J? it's a unit vector. Means the magnitude is 1. The magnitude is 1 unit. This x-axis, if it's inch, if it's pounds, if it's newtons, whatever it is, I don't know. Temperature, we're talking about vectors. If it's temperature, anything that it is, that magnitude is 1 unit. The direction of x and y. So we're going to use this to kind of have a better notation of writing vector f. So vector f is fx plus fy. This is a vector. This is a vector. This is a vector. fx I fy j. You see my notation changed. This whole thing is a vector. This whole thing is a vector because why? Because it has a magnitude and it has a direction. So you see that? So I'm still consistent. Vector plus vector. So we're going to use this notation I and j to kind of express a vector in a Cartesian form. So whenever we talk about Cartesian form or Cartesian notation, we mean I and j, and later we're going to add k to this. So I want to go back to this triangle here. So fx equal f cosine theta, fy equals f sine theta, fx squared plus fy squared equal f squared cosine squared of theta sine squared of theta. You all know this is 1. So x squared fy squared equals f squared. These are all magnitudes, all magnitudes. I don't need to remind you. These are all magnitudes. So f equals fx squared plus fy squared second root of that. So magnitude of f equals the second square root of the components squared. This is for if someone gives you the magnitude of fx and magnitude of fy and asks you to find magnitude of the force F. This is how mathematically you can find it. And if someone asks you, okay, if I have fx of this much, fy of this much, what is the angle that vector f is going to make with the axis? All you have to do is look in this triangle right here. Tangent of theta is fry over frx. So the angle theta is tangent inverse of fry. So here I just noticed I use a different notation. Just same as f. They just added an r, extra r. So if you have the component given fx or frx and fry, this is given. What you want, you got to find magnitude of f and its angle theta that makes with x-axis. So if those two are given, this is how you can find the magnitude of f and the angle between them. One other point that I want to mention is the angle or the direction of a vector, a force, is given 1 with an angle, and this angle could be with x or y, doesn't matter, or it could be with something that we call a slope triangle. So we don't have this theta, instead we have something called a slope triangle. They make something like this. They call it whatever, A, B, and then C. It's a little tiny triangle, A, B, C. So always in 2D format, they either give you a theta, either with x or y, or they give you a slope triangle. Theta we already looked at, right? Fx was f cosine theta. This is all magnitude. Fy is f sine theta in this case. Or let's say they gave you a different angle. They gave you this one, phi. Doesn't matter. You still have to use sine and cosine. In this case, fx is going to be f sine phi, and fy is going to be f cosine phi. So that's why I always tell my students, do not memorize this equation that as soon as you see fx, you always put cosine. It depends on which angle it's given to you. Now let's look at a slope triangle. Okay, in the case of a slope triangle, let's look at this little angle here. Let's call that alpha. Okay, cosine alpha is what? Is A over C. Sine alpha is what? Is B over C. So if, it's a big if, I had alpha, then I would have said fx equals cosine. If I had alpha here, I would have said f cosine alpha. If I had alpha, but I don't. Instead, what do I have? I have the ABC. So let's just replace the cosine alpha by its ABC. It's called, it's slope triangle. F A over C. Again, if I had alpha, I could have just said f sine alpha, but I don't have it, so I'm going to replace the sine with B over C. Okay, you kind of see the trend. When I want to find fx, I use A parallel to x. When I want to use fy, I use B, which is parallel to y. There is no more sine or cosine. There is nothing else. It's just magnitude of f, A over C, B over C. In the problems, we're going to see next video, when we start solving examples and problems, it gives you these numbers. It tells you it's 3, 4. It tells you the slope. It tells you how much x and y are changed. It doesn't matter if it gives you the third number or not, because you can find it. Right? You can totally find the third number. But so it's either it gives you a theta of whatever, 40 degrees, or it gives you a slope triangle. Just want to clarify that. So last thing I want to mention is something called coplanar forces resultants. So far you've learned how to add two forces together, right? A plus B equals R, or Fx plus Fy equals F. But in most cases in real life, we deal with something called coplanar forces. And that means coplanar has two words. It has a co and it's planar, that comes from plane. And that's all the forces that they lay in the same flat 2D plane. Look, here are some examples. The first one is just a hook with 3 forces. All of those forces are in x and y plane. All of them are in xy plane, so they're all coplanar forces. The second one is it's not a hook, some cables attached, maybe a truss structure, something like that. There are 3 forces, a 325 newtons, 600 newtons, F. Oh, look, it's a good example because here it gives you an angle of 45. So you have the magnitude and you have the direction. Here you have the magnitude. Do you have the direction? Of course you do. They give you a slope triangle. I didn't notice top, it was the same. Look at that 400. Magnitude 400, direction 30 degrees. Magnitude 300, direction x direction. Magnitude 250, direction slope triangle. And so one of them that is angle, you use sine and cosine. The other one, you just use the slope triangle relation. So let's get back here. Coplanar, bunch of other forces that they all, if you look at this picture in x and y, they all lay in x and y. Third picture, this is actually a tree that I planted a couple of weeks ago and has 3 sticks on it. This looks like a 3D, but if you think about a plane here, a flat 2D plane, and I don't know, let's call this x, let's call this y. These 3 forces that you are seeing, let me change the colors. So there is one here, there is a second one here, there's a third one here that kind of pulling this tree in 3 different directions. These all lay in a flat plane, and that's called a coplanar forces. The way to do this, so the goal here is to find the resultant. Sorry, these arrows are not showing the video, I don't know why. So I have 3 forces that are coplanar, meaning they're in a flat x and y, x and z, y and z, whatever it is, but it's a 2D flat plane. The goal is to add these 3 together, P, Q, and S, and find R. The steps that we take is first find components, Cartesian components, rectangular components of all 3 forces. So look, force or vector P now has pxi, pyj, pxi, pyj. These should all be arrows. So this is my P. Q has qxi, qyj, qxy, qij, and S, same thing, sxi, syj. Remember, this is magnitude, doesn't have arrow, but this is direction. This is a unit vector, so that one has an arrow. And look what they did. This needs to be arrow, this needs to be arrow. They put all the i's together, they put all the j's together. And that's what this means. Summation of all x's, everything that falls on this axis, they just mathematically add them together. And for fy, everything that falls in the y-axis, they add them together. And this is what you get. Step 3. Sorry, it's getting a little bit busy and messy. Step 3. The summation of all of that resulted in an Rxi and that. Can you guess what's the next step? See, the goal was to just find the resultant of all of this. The goal is to find resultant. So we got to use our equation that we had. Remember, the magnitude, you can find it by just taking the second root of the squares, sum of their squares of the components, and find the angle. In the next video, I'll be doing multiple examples of these vectors to kind of understand better the concept behind this. Thank you for watching.